Welcome to Chapter 2, The Molecules of Cells. Chapter 2 is going to look a lot like chemistry because, well, it's chemistry. This is the longest lesson and many times the most challenging for students. Ultimately, we are going to be looking at some very large biological molecules that are used to make up cells. However, before we begin that, we need to first examine atomic structure. Let's begin with some definitions. Matter is anything that takes up space and has weight. All matter is made up of elements. And we will be examining the atomic chart in just a moment and discussing the structure of atoms. An atom is the smallest unit of any element. This is a diagram of an atom. An atom consists of three subatomic particles. The first two are the protons and the neutrons. Protons are found in the nucleus of the atom. They have a charge of +1. They also have a mass of 1 atomic mass unit. Neutrons are particles that are also found clustered inside the nucleus of the atom. Neutrons have no electrical charge, and they also have a mass of 1 atomic mass unit. The third subatomic particle is an electron. Electrons have a negative charge of 1, and they are essentially weightless. Electrons are found orbiting the nucleus. Before we go any further, we need to learn a little bit about electrons and electron orbitals. Electrons do not just randomly circle about the nucleus, but they are found in specific electron shells. The innermost shell of an electron can contain up to 2 electrons. The second and the third shell can contain up to 8 electrons. The third electron shell can really hold up to 18. However, for our purposes, we are going to consider that third electron shell to be filled with 8 electrons. In this diagram, you see some protons and neutrons clustered in the nucleus and 2 electrons in that first electron shell. Another thing to remember about electrons and electron shells is that the shells will fill sequentially. What this means is the first 2 electrons will go into the first electron shell. If we continue to add electrons, they will then go into the second electron shell. So electron numbers 3 through 10 would be in the second shell. This would fill the second shell with 8, and subsequent electrons would go into the third electron shell. This is very important because it's the outermost electrons that determine the activity and the chemical reactivity of an atom. Atoms are going to participate in chemical reactions in such a way to fill that outer electron shell. Any atom that has a filled outer shell is stable. These atoms like to have a filled outer shell. We call that outer shell the valence shell, and the electrons in the valence shell are the valence electron. But again, if we know how many electrons are in that valence shell, and we know that the atom wants a filled shell, we can make some predictions about how the electron might behave in chemical reactions. Some additional things we need to know about elements or atoms. They all have a unique atomic symbol. We have here in this diagram the periodic chart of the elements, and you see the letter there in each of the little boxes. That would be the atomic symbol. Elements also have an atomic number. The atomic number is the number of protons found in the nucleus of the atom. This actually defines the element. For example, if we look at hydrogen, atomic number 1, it has 1 proton in the nucleus. If we change that number, it's not hydrogen anymore. If we add a second proton, it becomes helium, atomic number 2. Elements also have a specific atomic weight. The atomic weight is the number of protons plus the number of neutrons. Recall, the protons and the neutrons are the only particles that have weight. Electrons are largely ignored when calculating atomic weight. So, for example, hydrogen, atomic number 1, it has 1 proton. Its weight is 1, and so the most common hydrogen has no neutrons. Another one that we'll be looking at a lot in Chapter 2 is carbon. You see carbon is atomic number 6. So the atomic number tells us that it has 6 protons. Carbon also has 6 neutrons, and so the weight of the most common carbon would be 12. We call that carbon 12. Another thing that we need to remember, and this is very, very useful, is that atoms are electrically neutral. This is because an atom has the same number of protons, which are positive charges, as electrons, which are the negative charges. And so these balance out. So an atom is electrically neutral. In the next segment, we'll be talking about ions. An ion has different numbers of electrons and protons, and so it does have an electrical charge. But for now, we're only talking about base atoms, and they are electrically neutral, the same numbers of protons and electrons. Right. If you remember just a moment ago, we mentioned that the atomic number tells us the number of protons. So the atomic number also tells us the number of electrons. In our example here, this would be carbon. Carbon is atomic number 6, so it has 6 protons in the nucleus. Because it's electrically neutral, it also has 6 electrons. Now, we can use that information to do something called an electron configuration. We can place these electrons in the correct electron shells. Remember, the first shell holds 2 electrons, and now it's full. So subsequent electrons have to go into the second shell. So if you look in this diagram, that leaves 4 electrons to go into that second shell. Also, remember, we've already stated that atoms are going to react in such a way to get a filled outer shell. Carbon begins with 4 electrons in its outer shell. The second shell can hold up to 8. So carbon is going to behave in chemical reactions in ways to get 4 additional electrons. So we will look in the next segment at some chemical reactions, some chemical bonds, and see how carbon might accomplish this. An isotope is a variation in an element that has different numbers of neutrons. An example of a couple of different isotopes, one we just looked at, carbon 12. Carbon is atomic number 6, so it has 6 protons. Carbon 12 also has 6 neutrons, so the atomic weight would be 12, 6 plus 6. Carbon 14 also has 6 protons. Remember, that defines the element. If we change the number of protons, it's not going to be carbon any longer. But carbon 14 has 8 neutrons, so it has an atomic weight of 14, or carbon 14. Some nuclear arrangements are unstable. Carbon 14 is an example of that. Whenever it has 6 protons and 8 neutrons, that's an unstable configuration. And so these types of isotopes go through some radioactive decay in an effort to become more stable. And we call these radioisotopes. These are some Bohr models. This gives us an opportunity to practice a little bit of what we have learned up to this point. The first one that we see here is hydrogen. Hydrogen is atomic number 1. So it has 1 proton. It also has 1 electron. That electron is going to be in the first electron shell. Carbon, we looked at just a moment ago. Carbon is atomic number 6. So it has 6 protons. Also has 6 electrons. We put 2 of those in the first electron shell. That leaves 4 electrons in the second shell. So carbon is going to react in an effort to fill that outer shell, which happens to be the second one. So carbon wants to pick up 4 electrons. The next one, the top row over on the right, is nitrogen. Nitrogen is atomic number 7. It has 7 protons, also 7 electrons. So 2 of those would be in the first electron shell. That would leave 5 in the second shell. Nitrogen would like to have 3 more. That would fill the second shell with 8. We'll look at one more example down on the bottom row, back on the left, oxygen. We'll be seeing a lot of oxygen in some of the molecules that we'll be looking at. Oxygen is atomic number 8. 8 electrons. So that's going to be 2 in the first shell with 6 in the second shell. So oxygen will react in ways to gain 2 additional valence electrons. Let's look back at the periodic chart of the elements for just a moment. How many columns do you see? How many vertical columns? There are 8. The elements are arranged into these vertical columns, which are called group numbers, and each element within a group has the same number of valence electrons, which means they are going to react in similar ways in chemical reactions. The first column, group number 1, up at the top, we have hydrogen. We looked at hydrogen just a moment ago. It has a single valence electron. All of the other elements in group 1, lithium, sodium, potassium, also have 1 single valence electron. Everything in group 2 has 2 valence electrons, etc. If we move all the way over to the far right, group number 8, what these have in common is they all have a filled outer shell. Their valence shell is filled. Helium, for example, helium is atomic number 2. 2 protons, but also 2 electrons. Those 2 electrons will be in the first shell, but that fills the first shell. Right? If we come down the list, each of these, neon, argon, etc., they all have a filled outer shell, and that makes these atoms unreactive.